So, hello everyone, I'm Yuan from the EC department, and today I will give a brief introduction about some of the early explanation of the investigating how to apply the deep learning or machine learning technique into the design of the algorithm and hardware co-design for some important DSP module in the physical layer. So right now, the deep learning has become a very popular and important artificial intelligence technique. And essentially, deep learning actually is kind of the resurgence of the neural network. But right now, the deep neural network, they will be very large and very deep. And correspondingly, they can have a very powerful representation and learning capability. And based on those capabilities, right now the deep learning has been used in many applications, like the playing those games, Google's AlphaGo, used as the computer vision in the autonomous driving, the speech recognition, and also right now in many medical diagnostic tasks. And actually beyond that, so deep learning has already been expected and already been applied in many other application domains, like the storage, networking, finance, education, and according to this figure, actually this figure is kind of a little bit out of date. So because this prediction is based on it is in the 2017, and it is expected that by the 2024, if we just consider about the software side, the revenue of the deep learning based techniques the total market will be beyond about $10 billion. But obviously, so right now, this data is kind of out of date because just based on the same data from the same prediction from this company. So last year, they predict that for the hardware side, so deep learning hardware, the total market by the 2025 will be beyond $66 billion. So if we consider the software, it will be even higher. So from this figure, we can find that so deep learning already be used in many domains. So how about the communication, the networking? So from the view of the research side, in the research community, so for those the deep learning based exploration on the networking right now is already those efforts have been very active, and because right now we can have a lot of the data. And also for those the networking scenarios, typically it is in many cases it's very hard to model, and so we can use the data-driven method to solve this problem. But however, when we consider about the physical layer of the communication, so right now the research on the deep learning based effort is still kind of in very early stages, and although the machine learning. Generally, the machine learning approach has already been used in the physical layer for a long time, but for the deep learning, it is still in a very early stage. And right now, all over the world, there's several groups already working on this part and focus on some the components in the physical layer, like the channel decoder, the detector, estimator, and some equalizer, and so on. But in all worlds, compared to the very active phenomenon in the networking side, so for the physical layer of the communication side, so it is still it's a very emerging. So maybe you have a question. So why those researchers right now they are investigating the deep learning for the physical layers? So right now the physical layer we know that is very mature. So we have a very solid mathematical framework to help us to have a very highly reliable transmissions. So why we need those data-driven methods to do that? And so in general, so there are several potential benefits that if we can leverage the benefits of the deep learning and apply it to the physical layer design. The first that because this is a data-driven method, so it is kind of the model-free solutions. And in some scenarios, especially in the practical applications, sometimes it's hard to accurately model the channels. And in that case, maybe the data-driven approach is a help. And the second potential benefit is that, so in some cases, it may improve the BER performance. And for example, so for the channel decoding, so in the practical, when we want to design a LDPC decoder for the some product decoder, and we need to introduce some heuristic factors, like the scaling factors. Sometimes it will be 0.75, or sometimes or in the blip propagation decoder for the polar codes, the scaling factor will be based on a lot of the simulation, maybe the 0.875. But that's just kind of heuristic factors. And so some published record already show that, so if we can utilize the deep learning method to train those parameters, and for certain type of code that, so the BER performance can be improved. And this is because the deep learning actually it is good at to solve those when the heuristic factors exist in applications. If it's a very mathematical solid task, so then we don't need such method. But if you have some that in the work there's some factors that are very hard to use a very explicit mathematical language to model, and then in that case, those data-driven approaches may work. This is the second benefit. And the third one is that it potentially can provide those the online learning capabilities. So that means that when we want to provide some flexibility and reconfigurability to your underlying hardware, and then and the underlying DSP task. So when it is based on the machine learning or the deep learning, so it can be online updated, and in that case, it can provide such benefits. And the fourth advantage is that, so from the view of computation, so those neural network inherently they are highly parallelism. And in that case, so when some of the baseband DSP algorithm they are serial, for example, for the polar decoder in the 5G, so the underlying decoding algorithm is the successful cancellation list decoding. So inherently, it is a serial decoding method. Although we can try to improve its parallelism, but the overall decoding scheme is still serial. And in that case, so if we can completely drop this method and to replace a deep learning-based decoder for the polar decoding, and in that case, so such polar decoder will be highly parallel. And the last potential benefit is that, so the kernel computation of the neural network itself, they are kind of the hardware friendly. So the kernel computation of the neural network actually it's just the matrix vector multiplication or the matrix modifications. So from the view of the hardware design, it is very easy to design the hardware. However, for some DSP algorithm for the baseband processing, they are involved with the matrix inversion. For example, for the large scale MIMO detector. So typically, right now we can only use the MMSE, and actually for the MMSE, it is already has the inversion. So right now, we typically use the kind of the approximate matrix inversion, try to do some approximation. And also, if you want to use some more advanced MIMO detection algorithm like the K-BAS, those field decoding, so they also inverse they will introduce some complicated computations. And however, if we can redesign those components, use the neural network, so in that case, no matrix inversion will be used. And in that case, so we know that from the view of the hardware design, those are the matrix inversion or the Gaussian elimination. For those tasks, it is very hardware unfriendly. So as the hardware designer, we typically will try to avoid your task have such computations. So in that case, so the potential use of the deep learning to integrate it in this task, it can help to alleviate the burden of the hardware design. So that is some of the motivation that why we are interested of the application of the deep learning for the physical layer. But however, there are also some very challenges when we want to combine these two together. And the first, as I mentioned before, so actually currently those non-machine learning based approaches are already good enough in many cases. So we have the very solid mathematical framework for the physical layer design. And for example, especially for the channel coding side, so right now we already have very good theoretical proof that the capacity approaching, that is LDPC codes or topo codes, or even the capacity achieving, that's the polar codes already exist. So actually, there's very few space that we can play here to even or very little motivation that why we need to introduce those data-driven machine learning based channel decoder here. And another potential challenge is that the overhead. So the neural work, actually, it is involved a lot of the computation and the storage requirement. And on the other side, so unlike the networking domain, so the physical layer, it is extremely sensitive to the latency, to the power consumption, and to the area of your underlying hardware. And in that case, so we need to consider, we need to evaluate so whether it is worthwhile. Even the performance, the task performance like the BER performance, they are similar when we use the neural work. But the hardware overhead, whether it is tolerable to use this method. So I can give you quick examples of how big those neural work can be. So actually, these two examples, that is not for the communication, that is for the natural language processing and the computer vision. But we can still see that they are very huge. So for example, for very state-of-the-art natural language processing model, neural model from the Google, so it requires nearly 400 million parameters for that model. So that's very huge. So this is a very storage intensive method. And also for the very famous the ResLLR-Net, this kind of convolution neural work from the Microsoft. So for the ResNet 152, that is contains the 152 layers. So it requires the more than 11 giga macroration. So each macroration includes the one multiplication and one additions to process one images. So that is a very computation intensive examples. So we can see that the use of deep neural work, that is not free. So it may introduce a lot of the overhead. So when we consider that, to apply that to for example, for the physical layer design, so we have to consider those overhead and to estimate and evaluate that. So right now my group has already begun some very early exploration of apply the deep learning technique to the physical layer design. So our view of this field is that we must do the algorithm hardware co-design. That means when we propose some of the neural work based the DSP module for the baseband processing, so we must consider is the overall hardware complexity, the computation complexity, and the space complexity. And in that case, since the neural work is inherently very huge, so we must propose or apply some very efficient neural work model compression methods to do that. And also, when we design those algorithms, so we need to make it kind of hardware-friendly algorithm for the physical layer design. And such method, actually, we will use our prior experience in both the physical layer design and deep learning. So we have already done some very early work on the polar decoder when the polar decoder has not been come to the 5G standard. So starting from the 2011. And we also already done some works on both the deep learning algorithm and general deep learning algorithm and hardware co-designs in some, and published them in some the machine learning and the computer architecture conference. And next I want to introduce some more technical details. So generally speaking, so for current deep learning based physical layer design, so typically we have the two types of paradigms to achieve that. The first one is that it is I call that so-called deep learning added solutions. So that means that the underlying algorithm is still the classical algorithms. For example, for the channel decoder, when we integrate the information of deep learning, that the underlying algorithm is still like the belief propagation algorithms. But the key difference from the traditional method is that here we will reformulate the existing approach to the format of neural work. So that means in some cases we can view those traditional algorithms in the baseband processing, actually they're kind of the special case of the neural network. And in that scenario, that means that actually we can utilize some techniques in the neural network theory to help to improve the performance. And a very typical example is for the channel coding. And I will introduce that later. And typically such kind of the solution, I call that typically it will target to it is the module level solutions because it target to each individual module, like for the decoder or for detector and so on. And the second type of the solution, I call that the so-called deep learning enabled solution. So that is more aggressive strategies. So typically it's extreme case that, so for the entire receiver end, so we just use one neural network to do that. We just use one neural network to do that. And it's a totally end-to-end solution. So that is a very typical neural network style. And sometimes some people even propose that we even do not use some domain information, but I doubt that this can work. And a less aggressive method that, so we can we can throw away the original DSP algorithm for the baseband processing for some individual modules. For example, we can design some new code, some neural network-based codes for the channel decoder. And we can also design some new detectors, and that is also neural network-based. We do not use the zero forcing MMSC or like the AMP. Just neural network-based solutions to design some important modules. Or even further, we can design some unified neural network for for the intra-module design, like for the joint detector and decoder design. So we can just use the one neural network to do that. Since currently we already have that, we need to use the turbo operations to have the soft output detector and a soft output decoder to give soft feedback to the front end detector to do that. So that means actually we can replace the joint decoder and detector together and use a new neural network to do that. So that is another example for the deep learning enabled solutions. And now I will introduce some of early works. So one work is for the channel decoder, deep learning for the channel decoder. So right now, for some existing works that on the deep learning for the channel code, we know that actually, the current most popular belief propagation, the BP decoder, actually we can view that is kind of the folded neural network. For example, so this is a factor graph. This is a factor graph. This is the variable node, and this is the check node. So actually, typically we know that no matter for the LDPC codes or polo codes, actually we can perform some of the message passing along this the tensor graph to do that. But actually, from the view of neural network, actually for each iteration, actually we can unfold them to reformulate it to a feed-forward neural network. And here it is not just simply forward, because actually the node here, each node here, it will be not the node of your check node. Instead, it will actually be the nodes of each node corresponding to each edge. Because for the neural network, so each output node is just output one. It will just output the same values for its output. But for the belief propagation decoder, we know that no matter for each check node or each variable node, so actually its outbound message will be different for its different neighboring nodes. And in that case, actually it's here that each node in the corresponding unfolded neural network will be the edge. But in overall, it is still a feed-forward neural network, just have the different activation functions. And in that case, so actually we can find that such factor graph, belief propagation-based decoder, actually is kind of the special case of the neural network. And in that case, actually, we can use the classical backpropagation training algorithm to train this network and to help to improve the performance. And this is because classically, so each scaling factor for each edge here, they will be the same. They will be exactly the same. But right now, in the framework of neural network, so actually we can train them to make them, each of them will be different. And some simulation result already shows that for some, especially for some simple codes like the BCH codes and some short codes, it can have the BER performance improvement. But however, so those existing work already also shows that when we consider about like the LTPC codes or the Polo codes, so we cannot observe the performance improvement, unlike the BCH codes. Okay. And in order to address these challenges, so actually my group will propose the so-called the ResLLR-Net. So this is kind of latency-aware neural network added decoders. So, and here the key idea is that so actually we leverage the idea of the residual neural network in the neural network design to introduce the residual block into the neural network design for the channel decoders. And this is because, so we know that when we want to unroll your original belief propagation decoder to a neural network, so typically, so the entire depth of a neural network will be deep. Because typically we need at least 5 iterations. So 5 iterations means that corresponds to at least 10 layers. And we know that from the neural network theory, we know that when the neural network becomes deep, and it may suffer the vanishing gradient problem. And in that case, that actually it is hard for the neural network to learn, to update its weight. And in that case, so the performance will be not so good as we expect. But the good thing is that for the residual network, actually that is proposed by the Microsoft. So it introduced the so-called residual block into the design. And in that design, that it will besides the original feed-forward path, it will have another shortcut path to directly to transmit the previous input to the output layers. And in that case, actually, it can help to retain the local gradient. Will still have some magnitude, and in that case, it can help to accelerate the training and to help improve the performance. And based on this observation, we know that currently those existing deep learning-based channel code, so they just use the feed-forward method architecture to do that. And we believe that this is a potential reason that why when it applied to like the LTPC codes, performance is not, we cannot observe the obviously performance improvement. So we propose that we can also integrate such the residual block into the design of the neural network channel decoder. And we do some preliminary examinations on the short LTPC codes. And you can see that, so we compare that with the classical belief propagation decoder without using neural network. And when we use the neural network, we can see that actually its performance improvement is very minor. But when we introduce the residual block here, we can see that at the same iterations, we can have some of the 0.3 dB decoding gain. And it will be similar to a belief propagation when we have the more iterations. And this phenomenon said that, so actually using this method, actually we can help to reduce the latency. This is because that we know that LTPC is already a capacity approaching code. So typically, when we want to use the LTPC, typically we will require that it can achieve its maximum performance. And in that case, so utilize this method, actually we can still achieve the same BER requirement, but we can significantly reduce the required number of iterations. So that means correspondingly, we can reduce the latency. And this is our first preliminary work. And the second one is about the detector. And so right now, very state-of-the-art deep learning-based detector is the DetNet. That is from that is published last year from Israel research group. And so it's general method that, so actually it is kind of deep learning enabled solution. So it throw away the traditional MIMO detection algorithm. So it used the neural network to do that. And the key idea is that, so it used the projective gradient descent method to do that, and introduced some new layers for its so-called DetNet, the detection net, to perform the MIMO detections. And its performance is good. It can have a better performance for some the detector algorithm like the AMP or the SDR, and much better than the zero forcing. But however, the hardware complexity, its computation complexity and the storage complexity will be very huge, because we can see that so actually it will introduce the multiple weight matrix, the WK1, WK3, WK2, to be involved in the computation when it performed the MIMO detections. And in order to reduce the complexity, so actually we utilized our prior work on the general neural network compression, so-called use the Circulant matrix to reduce to compress the neural network model size. And here the key idea is that so actually when we consider weight matrix of your neural work, so we purposely to enforce some structures to the construction of the weight matrix itself. For example, to make it become the block Circulant matrix. And in that case, so right now we have some spatial pattern in your weight matrix, and then we just need much less, independent of the number of parameters, to store your entire models. And applying this method to this DetNet compression, so actually we also did some very early explorations, and you can see that for this is for 20 by 30 MIMO detection over the QPSK modulation channels, and we can see that so as compared to the original non-compressed DetNet, so it has some performance degradation. But when we want to compress it by 2 or 4 using our method, so as compared to the original, the approximate message passing based detectors, so in certain range of the SNR, so we can still have some of the SNR gain here. And also notice that here right now for this simulation we have not have a very carefully neural network tuning, and we believe that so such gain between this compression can be even reduced when we have the better tuning of the neural network, the compressed neural network. So this is still very early results. Okay, so some conclusions. So right now the research on applying the deep learning for the physical layer design is still at very early stages, but it's very interesting. And so including my group and some other group, we already have some very interesting observations and phenomena. And so potentially it can have this type of the research task have the potential huge impact. This is because the physical layer is so fundamental. So if the neural work, even just a part of them, can be utilized in the redesign of physical layers, so it will reshape the landscape. And especially consider that, so for those the modern chip, so typically for those baseband modern chip, they are the ASIC design. They are not based on the CPU or GPU. So they are highly customized to the underlying algorithms. So even part of them just revised. So the modern chip, the chip companies, they will correspondingly completely redesign the entire model. But however, the challenge is that the overhead. So neural work is computation intensive and storage intensive. So we must consider the overhead when we try to apply this method. This is the very hot deep learning method to these applications. And how to reduce the overhead? So I think there's some potential directions. So first, that how can we properly utilize also domain knowledge to the architecture design of the neural work? So a very successful example is that for the deep learning based channel decoders, actually for this type of the research, we properly utilized the underlying domain knowledge, the belief propagation algorithm is still the underlying algorithm. And we redesign the neural architecture, so the activation function will be different. And the topology of your neural network will be different. We do not just use a convolution network and so on. So this example shows that the proper use of the domain knowledge is very important to design some new neural architecture. And also, how to utilize the domain knowledge-based compression method is also very important. And the third one, I think, a very important and very promising direction is that when we want a good method to reduce overhead is that when we can consider more modules together to use the neural network to use the unified neural network to achieve the task of the multiple modules like the joint detector and decoder design. And in that case, the overhead can be significantly reduced. That is what I believe. Thank you.